Okay, pre-calc students, we are going to look at the domain of a function today, domain of relations, range as well. And I'm actually going to record one video that's going to talk about domain graphically and domain analytically. So that should be able to take care of two worksheets for you. Just a reminder, a function is a relation in which every element of the domain corresponds to exactly one element of the range. Your domain are your x values. They are your inputs. So the idea is that if you have all the numbers, negative infinity, negative 2, negative 1, 0, 1, 2. If you have all the numbers, which ones are available to use for the function or for the relation? Which ones are available? And then the y's are the outputs. And again, out of all the numbers that exist, which ones can you get out? So here's what I like to do, okay? A vertical line has an equation of x equals. And so if we drag a vertical line across this graph, it will tell us what domain values there are. So this is at an x value of negative 7, x value of negative 6, and now an x value of negative 5. And you can see I start to pick up domain values there. So negative 5 is part of the domain because the graph has an output. The output is 5. Now at negative 4 it has an output of 5. Now at negative 3 it has an output of 5. In fact, the domain is going to be from negative 5 to 2. But then I have a parenthesis because, sorry about that, I have a parenthesis because you can see you have an open circle right there. I continue to drag that across. Looks like right after negative 1, I start to pick up values again. So I have union, negative 1, all the way over to 4. Now, y equals, your range values, y equals produces a horizontal line. And so if I grab a horizontal line and I drag it starting from down here, I drag it up, you can see there are no graph values at negative 6, negative 5, negative 4, negative 3, but all of a sudden negative 2 I pick up. It's only at negative 2, and then it's only at 5. So therefore, you use roster notation in order to specify certain numbers, only these numbers. Only the number negative 2 and only the number 5 are outputs. Over here, domain. You can see that the graph is going to eventually go over here and go here and go here and go here and go here all the way till 4. So the domain is going to go from negative infinity to positive 4. The range, eventually the graph will come on down here. You can see it's got that arrow. It's pointing that way. And it goes all the way up until I get to 2. So the range will be from negative infinity to positive 2. For this line, always going to cross this vertical line here. So same thing with this horizontal line. So domain and range are both all real numbers from negative infinity to positive infinity. For this next one, you can see I don't pick up values until I get to 4. And then I keep values all the way until I get to 3. And for the range, I'm always going to have values down here, 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 arrow pointing up. We're going to have values up there. So the range is going to be from negative infinity to infinity. I really didn't name this very well. I talked about domain and range of a function. This is not a function because you can see the vertical line that exists there. The next one's not a function because, you know, again, it crosses the vertical line twice. And so, but you can still have domain and range without being a function, okay? So we're still determining domain and range. In this situation, you start picking up values. Well, we'll say 4. If the graph isn't perfect, just estimate. So we'll say 4 all the way to 4. Negative 4 to 4, excuse me. And then your range, we're going to, whoop, don't do that. I was doing so well. Oh, it's really not liking me. Come on, you can do it. Oh. There we go. And it starts at negative 6 and it goes up to 4. So negative 6 up to 4. Next one, you can see domain is going to be all real numbers. I have arrows on both ends, so it's going forever in both x directions. But for the range value, it looks like I don't have a value until negative 2, and it does go up to positive infinity. So there's a graphical representation of domain and range. You'd be ready now at this point to go ahead and do domain and range graphically. If you want to tune in still, you can pick up the domain and range analytically. That would be by looking at your other worksheet. So, as you look at the graph of x squared, you could tell, and this should go all the way down to 0, that the domain is going to be all real numbers, and that the range is going to be from 0 to infinity. But what I want to talk about, I don't want to focus on the range so much. I want to focus on the domain. So without looking at the graph, I want you to look at x squared and think about what you can plug in. For example, can you square negative numbers? The answer is yes. Can you square 0? The answer is yes. Can you square positive numbers? Yes. In fact, you can square anything. You come out with a result. So therefore, you have all available numbers to plug in for x. If you look at this situation, it's different. Hopefully you can understand that when you look at this, there's a certain number that you can't plug in for x. And some people might say 0. That's incorrect, because you'd have 2 times 0 over 0 minus 3, which is 0 over negative 3. That's a value. It is 0. The number that you can't plug in is 3. So you get 2 times 3 over 3 minus 3, which is 6 over 0. That is not a defined value. So therefore, we exclude 3 from the domain. So the domain is from negative infinity to 3, parenthesis, union parenthesis, 3 to infinity. You can see how it eliminates the value of 3 by using parentheses in those situations. Now, as you look at the graph down here, you could determine, as you look at the graph, you can see there's this thing down the middle. It's called an asymptote, a vertical asymptote that the graph approaches, but it does not touch. And it happens at 3 because the graph does not have an output at for an x value of 3. And so we could tell by looking at it right away. For the next one, you have a square root function. And as you see here, it starts over at negative 4 and it heads on this way. So by looking at the graph, you would say, well, it's from negative 4 to infinity. But if we were just to look at this, you would say, well, what kind of numbers can you not take the square root of? Can you take square root of positives? Yes. Can you take the square root of 0? Yes, the square root of 0 is 0. But you cannot take the square root of a negative. You can't. So therefore, because you can't take the square root of a negative, you could say, well, x plus 4 can't be negative. If it can't be negative, it must be greater than or equal to 0. And you would solve. You would say x is greater than or equal to negative 4, which is what we have there. So what you want to be able to do is you want to be able to think about domain without actually looking at the graph. You want to be able to look at the function rule. And if you have a polynomial, for example, say y is equal to x squared minus 3x, there's no restrictions. You can plug in whatever you want. Say you have y is equal to 5 minus x to the 8th. That's fine. In fact, if you have any polynomial listed like that that you normally look at, you're good to go. So if you see a polynomial, there really aren't any restrictions, and your domain is going to be all real numbers, or negative infinity to infinity. But then you have some rational expressions. For example, 1 over x minus 3. That has a restriction. You can't plug in 3. 1 over x squared minus 5x. Well, if you factor out the x, you would get 1 over x times x minus 5. There you cannot use 0 or 5. Those are issues, okay? You can't have 0 or 5 because those would produce 0 in the denominator. So there's all sorts of polynomials that will cause some problems for you, or all sorts of rational functions that will cause some problems for you. So you have to think about what produces 0 in the denominator. But then there are some rational functions that don't have restrictions. For example, 1 over x squared plus 1. There's no way that you can plug in something for x, square it, add 1, and get 0 in the denominator. There's no number that works there. So sometimes people look at the polynomial or a rational function. They say, well, I see a rational function, so I must have to eliminate something like 0 over 5. Nope, that one's okay. It's good to go. In fact, if you had, say, 2x divided by, again, something else that would be positive, say x to the 4th plus 3. Again, the bottom can never be negative, so you're okay. I'll add another one down there in a second so that you can understand, but there are some that will not produce any 0 in the denominator. Radicals, so the square root of x, can't have negatives. Square root of x minus 3, can't have values that are less than 3. The fourth root of x plus 2 can't have values that are less than negative 2. So every time somebody sees a radical, they're like, well, you're going to have restrictions. That's not true. Here's a radical that doesn't have a restriction. The square root of x squared plus 1. Because x squared plus 1 will always produce a positive. And you can always take the square root of a positive. Here's another one. The cubed root of x minus 9. You can take cubed root of negative numbers and positive numbers. So cubed roots are okay. I told you I go back to the rational one. How about this? 3x over the square root of x to the 4th plus 2. Looks like a crazy function. When you look at it, you say, oh, this is always going to be positive. It'll never be negative, and it will never be 0. So all real numbers would suffice there as well. All right, so this, for a lot of people, is a complicated section. So it's going to be very important that as you look at your work that you don't just peek at the answer key all the time, but rather if you're getting problems wrong, that we decide to Google Meet and go over some of these problems, okay? So I don't have the graph now. I just look at the function. Square root of x plus 2. I know you can't take the square root of negatives. So therefore, I say x plus 2 must be not negative, or x plus 2 is greater than or equal to 0. We solve that, and we get x greater than or equal to negative 2. So my solution is negative 2 to infinity. That is my domain. Those are all the available numbers we can plug in. Now, you want to check your answer? Excellent mathematicians always know how to check their answers. Take a number in here, plug it in, like 0. The square root of 0 plus 2 is the square root of 2. You got an output. Try negative 3. Square root of negative 3 plus 2 would be square root of negative 1. That's I. That does not give a valid output. So negative 3, you can see, does not work. And you showed that in your domain. So you can always, always, always have a way to be able to figure out what works and what doesn't. The next one, x squared plus 3. That's a polynomial. Is there any number out there that you can't square and add 3 to? Can you square negative numbers and add 3 to it? Can you square positive numbers and add 3 to it? Can you square 0 and add 3 to it? Yes. So this is simply just all real numbers. But the next one, uh-oh, it's a rational function. And remember, for rational functions, you don't want to divide by 0. So what would give you 0 in the denominator? It would be 4. So negative infinity to 4, union with 4 to infinity. Sometimes you get tired of writing that, so you just want to write x can't be equal to 4. That would be fine as well. I will accept that. Oh, number 12, you see a cube root, and you're thinking to yourself, well, cube roots, that must be an issue. Nope, you can take the cube root of anything. Watch, the cube root of negative 8, it's negative 2. The cube root, whoops, sorry, that was square root. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of positives are positive. Cube root of 0 is 0. Cube root of negatives give you negatives. Doesn't matter what you plug in, you're going to get an output. So therefore, the domain is all real numbers, negative infinity to infinity. If you'd like to write this, that's fine as well. Next one's a rational function. Uh-oh, can't divide by 0. What will give you 0? Well, if you factor out the x, you get x times x minus 5. So x cannot be 0 or 5. Fourth root, hey, if it's an even root, it causes problems. If it's an odd root, no problem. So you can't take the fourth root of a negative, okay? So 7 minus x must be greater than or equal to 0. Subtract the 7. Negative x greater than or equal to negative 7. Divide by negative 1. X is less than or equal to 7. So negative infinity to 7. 15. A lot of people look at 15, they're like, well, x can't be 5. And I ask why, and they say, well, because that would give you 0. Folks, it's fine to come up with 0. You just can't get 0 in the denominator. This is just a polynomial. It's a line. Slope of negative 1 goes through 5. Domain is all real numbers. Uh-oh, rational function. Well, it's kind of a rational function, but it's actually just a polynomial as well. It's 1/5 x squared minus 1/5. You can't get 0 in the denominator. The denominator is always 5. All real numbers. Next one, rational function. Wow, let's factor the bottom. Oh, look at that, x squared plus 1. There's no way that the bottom can ever be 0. All real numbers. If you get caught up in like, oh, well, I need to know what to do when. I need to know when I need to factor. I need to know when I do this, when I do that. I'm sorry, folks. As we get to the analysis of algebra, you have to think about what the problem is doing and what it's asking for. And I know that that's complicated. I know it is. But just understand, we got to break through that idea of just tell me what to do when, because it doesn't always work like that. Square root, problem. I have to make sure that I don't take the square root of a negative. So 3 plus 2x minus x squared must be greater than or equal to 0. Ooh, good thing we had that problem on your last test. I'm going to multiply through by a negative. X squared minus 2x minus 3 is less than or equal to 0. We're wondering, when is that less than or equal to 0? Let's consider the graph x minus 3, x plus 1, less than or equal to 0. If you think about that, it crosses through 3 and negative 1. When is this graph less than or equal to 0? Well, here it's positive, here it's negative. So it's less than or equal to 0 between negative 1 and 3. That is my solution for the domain. If you want to try, plug in a value. If you plug in 0, you get the square root of 3, and that's a valid result. If you tried 4, it would not work for you. Okay, you can always try values and see how they work. Look at the next one. Again, you can't have the square root of a negative. Well, let's look at the graph. X squared plus 2 is greater than or equal to 0. Some people say, well, that doesn't factor. It doesn't have to factor. Think about the graph. X squared plus 2, it goes up. It's shifted up 2 units. The question is, when is this thing above the x-axis? Always. So all real numbers work. Next one, negative 3 minus x squared. You say, oh, it doesn't really factor. Because again, you can't take the square root of a negative, so this must be greater or equal to 0. Sketch the graph. Go down 3. It's a negative x squared, so it's upside down. When is that greater than or equal to 0? Never. No solution. And For domain, actually what we write is we write empty set. Okay, you write no solution too. It's fine. This is actually technically more accurate. It's a null set. There's no available values that we can use. All right. Now we got you thinking. Look at the next one. We got two problems here. We've got the top, so the square root of x plus 2, and we got the bottom, x minus 3. Now you know x can't be 3 because you can't have 3 in the denominator. But look at the top. You would say x plus 2 must be greater than or equal to 0. So x is greater than or equal to negative 2. Well, think about these, folks. If you were to graph them, they are in conflict with each other because that's x greater than or equal to negative 2, but then you're saying that x can't be 3. So therefore, the domain is negative 2 to 3 union 3 to infinity. And that's how we eliminate 3. So you really must express your domain solution like that. The next one, you look at the top, you're like, well, x plus 4 must be greater than or equal to 0. So x is greater than or equal to negative 4. So we look at that graph. You can see that the arrow goes off that way. As you look at the bottom, you're like, cube root, so no problem, right? No problem. Except there is. Just remember, you can't divide by 0. Is there something that would give you 0? Yeah, x can't be 2. 2 would give you 0. So even though the cube root is okay, just realize you can't divide by 0. So we're going to eliminate 2 from our domain. So we have negative 4 to 2, union 2 to infinity. Folks, I know that this is not an easy lesson for some people. Some people really struggle with this. Don't give up. Sit down, talk with me, Google Meet. We'll talk through any problems together, and after enough practice, trust me, you will get it. You will get it. And we do come back to it. This isn't just a one-time thing. So definitely going to have some problems like this on the test. I hope that was informative. 22 minutes. You have a great day. You're now ready to do those 2 worksheets.